Dear students, welcome to the online class. I am Dr. S.C. Hiramat. In this video, you are going to study about the enzyme catalysis. In the previous video, we have studied about the homogeneous catalysis in that the acid-base catalysis. In this video, you are going to study about the homogeneous catalysis in that the enzyme catalysis. Enzyme catalysis was studied by the Michaelis and menten in the year 1913. Enzymes are the proteinous materials which work as catalyst in the biochemical reactions. Now let us study about the mechanism proposed by Michaelis and menten. Mechanism. Here S is a substrate or reactant. It reacts with enzyme. E represents enzyme and forms the intermediate complex, that is Se. Intermediate complex Se, and it takes place with rate constant K1. And that intermediate complex dissociates to give the reactant S and the enzyme E with rate constant K minus 1. We may call it as the step 1 and step 2. This is equation 1. In the second step, that is intermediate compound, that SA dissociates to give the product and enzyme is released, and this takes place with rate constant K2. We may write this equation as A2. Now here the intermediate complex is formed by this equation and absorbed by this equation and absorbed by this equation. Thus we can apply the steady state principle to the Se. Applying steady state approximation to ES, we get that is DES divided by dt, that is change in concentration of the intermediate complex ES is taken equal to 0. This is equal to formation of intermediate complex, that is equal to K1 into concentration of ES into concentration of E, minus the intermediate complex decomposes by this equation, that is minus K minus into ES, intermediate complex concentration, and it also decomposes to give the product by this equation, minus K2 into concentration of ES. Here the concentration of the enzyme taken is very small. Then the total enzyme present in the reaction mixture equal to free enzyme and the intermediate complex formed. Therefore, enzyme taken, the total enzyme taken E0 equal to E plus ES, that is intermediate complex formed. Only these are the two species in the reaction mixture. Therefore, E0 equal to this. Therefore, we may write E equal to E0 minus ES, E0 minus ES. Okay, thus we can substitute this in this equation. Okay, by substituting this in this equation, we get this DES divided by dt is equal to K1 into S, E equal to E2, that is E0 minus square bracket of ES. Okay, we can take the both combined flower bracket. Then minus K minus ES and minus K2 into ES, concentration of ES. Thus we may write this equal to K1 concentration of S into concentration of E0 1. Then another one K1 S minus ES. That is K1 concentration of S and the concentration of ES. Concentration of ES. Then minus K minus concentration of ES minus K2 into concentration of ES. Concentration of ES. Okay. Then we can make this equal to 0. This is equal to 0. We are applying the steady state principle. On rearranging this, or let us take ES as common. Then we may write ES is equal to this term remains as it is, K1 into S into E0 divided by, and ES is taken common from this, and we take the opposite side, all these become plus. Then we may write K2 plus K minus plus K1 into concentration of S. Concentration of S. We may take it as equation 3. Means by the approximation and applying the steady state principle to this, we get the concentration of intermediate complex formed, that is the ES. Then rate of the reaction. Then we may write rate of the reaction, that is rate is equal to what? The rate of formation of the product, that is D of product divided by dt. This is equal to K2 into concentration of SE, concentration of intermediate complex formed. Therefore, we may write rate R equal to K2 as it is, and ES you take from this equation. Okay, from equation 3. From equation 3 we may write, from equation 3 and 4 we may write it as the equation 4. We get rate equal to K2 into concentration of ES equal to K1 into concentration of S into concentration of E0 divided by K2 plus K minus 1 plus K1 into concentration of S. Okay. Then by dividing the numerator as well as denominator by K1, you are going to get K2 into S into E0 divided by K2 plus K minus divided by K1 plus concentration of S. Concentration of S. Here K2, K minus 1, K1 all are the constants. Thus we may write rate equal to K2 into concentration of S into concentration of E0 divided by, we may substitute by this another constant Km. K2 plus K minus 1 divided by K1 equal to Km plus concentration of S. Okay. This equation is known as the Michaelis-Menten equation. Okay. That is Km is Michaelis-Menten constant. Michaelis-Menten constant. And the equation 5 is known as the Michaelis-Menten equation. That is rate equal to K2 into concentration of substrate into concentration of E0 and then Km divided by Ks. Okay. This is the expression for the rate of the enzyme catalyzed reaction derived according to the Michaelis and Menten. Now we want to study about the other things. Here we may remove this rate of this reaction. And we get the maximum rate of this reaction. Maximum rate. Okay, suppose we want to write maximum rate. Maximum rate. And we get, and the means according to this, rate of this reaction is directly proportional to the concentration of intermediate complex formula, that is SE. And this is maximum, rate will be maximum. Okay, that is maximum when all the substrate, the enzyme is converted into this. Means that is rate is maximum when ES is equal to E naught, means enzyme taken initially. E naught is the enzyme taken initially, ES is the enzyme formula. In that condition, rate is maximum. Okay, rate is maximum when the concentration of the intermediate complex is equal to concentration of enzyme taken initially. Then we may write this rate maximum as the velocity maximum. Okay, and what is its value? We may take here from this last equation K2, that is from this equation, that is equal to K2 into concentration of E naught, concentration of E naught. That is rate maximum, or this is velocity maximum, when this SE is equal to total concentration of the enzyme taken, that is equal to K2 into E naught. Now this is equation 6. Equation 6 gives the expression for the rate of the reaction when it is maximum. Now we can apply some conditions for this equation. Okay, when that is when Km is very greater than concentration of S. Okay, then equation 5 becomes what is that? Rate is equal to K2 into E naught into S divided by Km. Okay, then E naught is the concentration of enzyme taken initially. This is constant. Km is constant and K2 is constant. Thus we may write this equation as some other constant into concentration of substrate. Okay, then we say that when Km is greater than, very greater than the concentration of S, the reaction follows. The reaction is of first order. Okay, the reaction becomes first order and the concentration of Km is very large, or the concentration of S is negligible compared to the Km. Okay, then other case. Similarly, we can apply the other cases. That is when Km is very smaller than, when Km is very smaller than S, very smaller than S, then equation 5 becomes, this equation becomes, what is that? Rate equal to K2 into E naught into concentration of S divided by, and Km is very small, you can neglect this, only you can keep this S. Then this S gets cancelled. Then R is equal to K2 E naught. Okay, and E naught is constant, K2 is constant, which is equal to V max, from this equation. K2E equal to V max. This is equal to constant. This is equal to constant. Means the reaction becomes zero order. Reaction becomes zero order. Zero order. Okay, zero order. Then another condition. Okay, here we are applying the conditions. Okay, this is first, and this is second, and this is third, and fourth condition is when Km is equal to concentration of S. Km is equal to concentration of S. In this equation, if Km equal to S, that becomes rate equal to K2 E naught. Okay, concentration of E naught into S divided by, you may, when Km equal to S, then Km plus S becomes 2 into S. Then this S gets cancelled. Then that becomes K2 E naught divided by 2. Okay, then that becomes that is rate equal to 1 by 2. K2 E naught is nothing but the Vmax. Okay, in this way we can apply the various conditions to get the different order reactions and different shapes. Thus, this can be explained with the help of a diagram. That is rate versus concentration of S. Along the x-axis, we may take the concentration of S, and here we may take, that is rate. Okay, then we are going to get a curve of this nature. Okay, now when R is maximum and E equal to S, here this is R equal to, that is R equal to Vmax. Okay, Vmax means this, in this condition, this is zero order. Okay, this is zero order, and means by further increase in the concentration of S, there is no increase in the rate of reaction. Initially, from this point, the rate goes on increasing. After that, when it reaches this, means this much concentration, that order becomes zero. Then another condition, when Km is greater than S. Km is greater than S. Suppose this is a point. We want to calculate S. S is smaller, Km is greater. Means in this area, when this becomes first order, that is first order in this area. What it means? If the Km is larger, suppose this is S, Km is larger, means Km becomes this side and S becomes less than this, means S becomes less than this first order. Now suppose in this case, at this point, Km is equal to concentration of S. Then what happens? Km equal to concentration of S, that is E, that is equal to 1 by 2 Vmax. This is 1 by 2 Vmax. When Km is equal to S, suppose at this point, if this is S and Km is also with the same value, then you are going to get this is equal to half of this. Thus, we can apply three conditions. When Km is equal to S, and when Km is larger than S, this is first order. Initially, Km is larger than S means S is larger than S is smaller than Km, the reaction is first order. And another condition, and this we get the R max, that is when the concentrate all the catalyst is converted into the intermediate complex, thus it becomes the zero order reaction. Okay, this is zero order reaction. The maximum velocity and the maximum rate is there, then the reaction becomes zero order. This reaction may be first order, may be zero order, or in between them there is fractional order. This is about the condition. Then another one about the verification of Michaelis-Menten law. Verification of Michaelis-Menten law, or verification of constants. Verification of constants. Now, what is the Michaelis-Menten law? Michaelis-Menten law, that is R equal to that is K2 into E0 into Es divided by Km plus concentration of S. This is Michaelis-Menten equation. Michaelis-Menten equation. Rate equal to this. Now we want to verify whether this particular reaction follows this rule or not. If it follows, we get straight line, and from that we can calculate the all other constants. Now you make the reciprocal of this. 1 divided by R equal to what? Km divided by K2 into E0 into S plus S divided by Km K2 into E0, K2 into E0. Okay, this is equal to Km. K2 into E0, we may take it as the V max into, that is S, concentration of S, plus this S gets cancelled. Okay, then you are going to get S divided by, means 1 divided by S gets cancelled. This 1 divided by V max. We are going to get. Now, what are the variables in this equation? V max is constant, Km is constant, this is also V max constant. Okay, this is also V max constant, and R is variable. Thus R and S are variable, and it is similar to the equation of a straight line, y equal to mx plus c. Thus we may plot a graph of this nature. Okay, of this nature we are going to get. This is 1 divided by S, 1 divided by S, and here 1 divided by R, rate, 1 divided by rate. Then we get a straight line with positive slope. All these are positive, means we are going to get a straight line with positive slope in this way. Okay, we are going to get the positive in this way. First thing, what about the slope of this reaction? Y equal to mx plus c. Y equal to mx plus c means here slope is equal to Km divided by V max. V max. Okay, V max. Then V max means K2 into E0. K2 into E0. If you know the E0 and K, we can calculate the K2. Then what about this Y intercept? Y intercept means when this part becomes 0. When this part becomes 0 means at this point, this is equal to 1 divided by V max. 1 divided by V max. Okay, 1 divided by V max. This is Y intercept. Then what about the X intercept? from this point to this point. From this point to this point means at this point r equal to 0. R equal to 0. R goes on decreasing and at this point becomes equal to 0. When it becomes 0, then this and this gets cancelled, and we are plotting a graph of 1 over S versus this Km. Then we get only this. Okay, then you are going to get this is equal to minus 1 divided by Km, minus 1 divided by Km. This y-intercept equal to my n divided by Km. Means, how do you evaluate this? Here, this is equal to 0. Means we make this equal to 0. Then you can take this side. That is 1 divided by S remains 1 divided by M. And this equal to minus value, you are going to get the minus value. Okay, here minus S and this is minus Km. This distance is 1 divided by Km. Means, if we first thing, by plotting a graph of 1 divided by rate versus 1 divided by substrate concentration, if we get a straight line, we say that this Michaelis-Menten law is verified, or the reaction mixture follows the Michaelis-Menten law. Then we are going to get one slope, one y-intercept and one x-intercept. Slope equal to, from this equation, Km divided by Vmax, and intercept equal to 1 divided by Vmax, and intercept y-intercept means x equal to 0. This part equal to 0. And x-intercept means y equal to 0. That is 1 divided by r equal to 0. Thus, you are going to get the minus 1 divided by Km.